Okay, we're going to talk a little bit about common projection systems and some of the background information that goes into that to make it maybe a little more understandable. So the most commonly used coordinate systems are geographic coordinate systems, the UTM or the Universal Transverse Mercator System, and the state plane system. Geographic coordinates, degrees of longitude and latitude. UTM, the world is divided into 60 zones, each one 6 degrees wide. State plane, every state has one or more zones. Typically larger states have more, smaller states have fewer. And the thing about the UTM and the state plane that we have to remember is within an individual UTM zone or within an individual state plane, distortion is minimized. And so for all intents and purposes, there's no tangible, reasonable, excessive amount of distortions to worry about in those zones. As you move outside of the area that the zone is supposed to represent, distortions increase and become increasingly more visible. Within each of these UTM zones or each of these state planes, the distortion is the least in the center. It is the highest, typically, along the edges. But nowhere in the zone or the plane is the distortion significant enough to really worry about it. So when we talk about geographic coordinate systems, why do we even have data in that? We're always using projected data anyway. Well, it's for distribution purposes. When you start changing data and projecting it again and again and again, you increase opportunities to add errors and create other kinds of distortions. And so we don't want to do that. So if we give you the data in a GCS, you can project it into a PCS. It's a geographic coordinate system projected into a projected coordinate system. Then you'll make one change and it'll be exactly the way you want it. The other reason that we don't use GCS, geographic coordinate systems data, for analysis and mapping is because it creates some significant distortions, and that is a problem for a lot of analysis. One of the big ones we use is the UTM system, Universal Transverse Mercator. What is it? It's a cylindrical projection. It's in the transverse position. In other words, instead of going up and down, it goes sideways. That allows you to then rotate the cylinder around the planet, and the contact between the cylinder and the planet will move as you rotate it. And what we've done is divided the globe up into 60 zones. Each one is 6 degrees wide. And so we number them off, and so when you're within a zone, the distortions from this projection are almost nil. As you move outside the zone, distortions become significant. But as you can look at the map and see, that creates some problems. For example, look at Texas. Texas is in 3 zones. Not a lot you can do about that. Louisiana is in 2 zones. But Louisiana is not as big as Zone 15. If only you could shift Zone 15 a little bit, it would fit. Turns out you can. State plane system is another really common one. And basically each state is divided up into one or more zones. They have these unique identifying numbers that identify the zones. And within those zones, they create a projection with its own parameters that are designed to achieve the best and most accurate projection of data in that area. And typically we're looking at transverse Mercator, Lambert conformal conic, and oblique Mercator as some of the projected coordinate systems that go into the state plane system. But for the most part, state plane system data is in feet, but some is in meters. But in general, if we see feet, we think state plane. If we see meters, we think UTMs. Here's a map of the state plane zones, and you'll kind of get some idea. Notice how some of the state plane zones like Texas run uh, left to right, sort of stacked in layers. This east-west configuration typically is a projected coordinate system. We'll typically use a projected coordinate system like Lambert conformal conic that works really good in something like this. So that's something that that state plane might use. Other states like Georgia, where they're divided east to west on a north-south axis, um, that's usually going to be something in the UTM system that they would use. How do you choose a projection? It's a really good question. Well, the first thing you got to do is realize that if you're in a GCS or a PCS, it makes significant differences in how things appear, how far apart things are, which directions things are, the lengths, the sizes, and the areas of things. Just look at how different the US looks between a GCS and a projected coordinate system. So when we think about the projected coordinate system, we have to think about what that actually means. Some are cylindrical, some are conic, and some are azimuthal. Cylindrical work good for north-south oriented. Conic works good for east-west. Azimuthal works for flat areas like the poles. Projections for large-scale maps. Remember, large scale covers a small area, so we're talking local city and county maps, maybe even small states. Projection systems virtually eliminate all the distortion at this level. So if you choose the right UTM in the state plane for your location, no problems. But remember, your location should fall in a single zone, because if it doesn't, the areas outside the zone are going to experience some distortion. Small scale maps cover large areas like continents and countries, and when you do this, distortion is inevitable. So you need to choose projections where the distortions won't create problems for your analysis. Equidistance maps is what you would use when you're looking for something where distance matters. Equal area when you're looking at areas. Conformal or compromise projections are just good general purposes. But ultimately, you got to select the projection that creates the least problems for your analysis. The software does something called on-the-fly projection that is both a blessing and a curse. It's wonderful in that it allows you to take data that's in different projected and geographic coordinate systems, add them into your data set, into your map document, and it will read what they are and automatically reproject that on a temporary basis to what the data frame coordinate system is, and then use that to properly display them alongside one another. But it does not change the projection. So you got three different data sets, one state plane, one UTM, one to GCS. It reads them, it knows what they are, it makes adjustments and displays everything together like they're playing along nicely like they should. But remember, the data is still in three different coordinate systems. When we look at our data, there's different kinds of units, and the first one we're going to talk about is storage units. Storage units are the units associated with the information that is stored in the actual data file itself. So every feature stores its XY values based on a specific coordinate system. And whatever that is, that's what the storage units are going to be. If it's a geographic coordinate system, it's going to be in decimal degrees. If it's a projected coordinate system, you're looking at meters or feet. This cannot be modified inside the feature class file. Map units are the units associated with the map document. These are set by the properties of the map itself, and they are what the software converts from what is stored with the data. And the third and last sort of units is the display units, and these are ones that you can set and change, and these are the ones that are displayed on the map or when you use tools to identify things on the map. You can go to data frame properties and set the display units. and they'll show up on the software in whatever form you set them. You need to understand the units and be careful not to confuse. The stored units are the properties of the files of the coordinate system that are actually stored with the data. The data frame map units are the units associated with the map itself. The display units are what you see with some of the various tools, and those are ones that you can change at any time. And basically it's all a big translation game, if you will. The data has its own units. The map has its own units that are basically translated from the data. And then you can change the display to show another set of units that could be the same as either one or different than either one. Okay, let's talk about projecting data. Permanently projecting data creates a new spatial data file. It does not change the original file. It takes every pair of XY points in the old data set. It gives them new coordinates and new units and creates a whole new data set in a different coordinate system. There are lots of ways to do it. I'm only going to kind of focus on the basic stuff. But we have wells information, two data sets. The one on the left is in a GCS. We want it in a UTM. We use the project tool. We get a new data set of wells, but instead of having those GCS numbers, we now have the UTM numbers. We do this using the project tool. In the project tool, you simply select the data, identify the coordinate system you want it to become. If you're changing datums, you have to select a geographic transformation, and then tell it what folder you want the new file to go to, and it will create it. There's also a bunch of shortcuts. You can export data, take data that's already there, click on it to export it, and you can do all the features or only the selected features, and then you can tell it what coordinate systems you use, the same as the layer, the same as the data frame, or you can select something else. And so this is another means of creating a new file with a different projected coordinate system, or a different coordinate system, period. You can also go in and set the environments setting on some of the tools, and when you do things like, for example, go from a feature class to a feature class, or do a clip or some other kind of analysis, in the environment you can say, make all my output in this coordinate system. Another shortcut. But honestly, starting out, you're best to just focus on doing it the simple, easy, straightforward, manual way and not try to use these shortcuts. But it's important you know they're there. A featured data set in the geodatabase has a defined coordinate system. All feature classes placed in it are automatically projected to match it. Rasters are slightly different. Basically, you got to know the XY location and the cell size. The XY location in the upper left dictates where the raster sits, and the shape of it comes from the projected coordinate system information, and then it then knows how to properly arrange and display it. When you have rasters in geographic coordinates, it creates significant distortions that are problematic. When you are in a projected coordinate system, a lot of times you get some bending, if you will, of the raster. But remember, the raster is all about perfect little squares, and so you end up with some areas that don't fill in, and that's fine. Here we have an example of what they call a local raster. When you get to smaller levels, something in a UTM zone will look like it does on the left, but if you're in a state plane zone where it might be more of a conic projection, it's going to align to that sort of curvature, and you're going to see a raster that looks more like the one on the right. Individually inside the data set, you won't notice much difference. It's only along the edges that you'll begin to see that it's slightly different. Georeference raster is one that already has coordinate system information with it and knows how to display it and how to set it up. If it doesn't have this, you have to add it. More examples about how it works and how you can do it, and you can create the files to go along with it, and it's a fair amount of work. You can also georeference things by finding another data set of the same or similar locations and point out coincident locations. In other words, the same physical space on two different data sets and say this matches up to this matches up to that. They call setting up these matched pairs as control points, and then the software will do mathematical wizardry and magic to bend, twist, spin, and otherwise align those identified points. The process of rectification basically permanently transforms it to a new image, and so it literally takes the old raster data set and makes a new raster data set that lines up according to your control points. And when you do this, you have to make some pretty significant changes at times, and this will create a brand new data set. We can evaluate how well we do at this by looking at things like the root mean square error. This is just an average difference between where the point is and where the point should be. This is not the end all be all number. You can make it lower by only selecting a couple points. You can make the registration, in other words, how well the data lines up, by adding more points. In a perfect world, you add a bunch of points scattered all across the area, and you see how it looks. You go back in and you take out points that have bad residuals, high residuals that don't line up well, and you add new ones in areas where you maybe don't have as many points. The second sort of process in that rectification is resampling. Once it aligns and creates the new grid, it has to populate it with information, and it does so by pulling information from the old data set to populate the new one, and that's called resampling. Three common techniques: nearest neighbor, bilinear, and cubic convolution. Nearest neighbor finds the cell value in the old data set that's located at the center of the new one, and that's what it assigns to the new cell. Bilinear is a little different. It starts off at the center of the new cell and identifies the four closest centers of the old cells, and then it calculates a distance weighted average to figure out what the new value of the new cell is in the new data set. So, quickest way to explain it: four closest cell centers to the new cell center, distance weighted algorithm to figure out the new value. Cubic convolution follows the exact same sort of premise as bilinear, but instead of looking at the four closest, it looks at the 16 closest. What does all this mean? Nearest neighbor preserves the most amount of information from the original data set. Bilinear, because it looks at four cells instead of just one, kind of gives you a little bit of a smoothing or a blurring of your data, and it's a little bit slower than nearest neighbor. Cubic convolution is the slowest, most time consuming, and it also is the one that blurs or smooths out your data the most. So when we do the projecting rasters, it has its own tool. The project tool and the define projection tool, they're designed primarily for vector data. The project tool will simply not work on a raster, and so you have to use the project raster tool. Now, from a GCS, you can estimate cell size. This is not something you need to spend too much time worrying about, except know this: a single degree change in latitude is equal to 111 kilometers on the ground. So think about that. If you're off by a degree in your recording of a known location in a GCS, you're off by 110 kilometers. Let that sink in.